Alright, so let's see an application or an example of free undamped motion that we discussed in last video. Alright, so now we have to read the question very carefully, and the units are very tricky in these type of problems. Okay, so let's read the question carefully. The spring constant of a 24-inch steel, okay, so that means the spring is 24-inch long, okay, and is measured by hanging a one slug mass from the spring and observing that the spring stretches 3 inches. Okay, so when you hang this mass, the spring instantaneously stretch 3 inches. So we do this experiment. So this is an experiment. One slug is not the actual mass that you're going to let the motion happen. So it's just we try to play with the Hooke's law. So we have a one slug and we are trying to determine K really, okay, and it stretch from 3 inches, okay, and now the half a slug mass is attached to the spring. Now you remove that one slug, now you attach a half a slug mass. That is what we let the motion happen, okay. So the mass is pulled down 3 inches and released with a 1 feet/second downward. Okay, so let's get into that later. But you have to work with American units. Okay, so 6 inch is represented by half a feet, so we will have to write everything in feet. Okay, and so that means 3 inches is actually 1/4 feet. If 6 is half of 6 is half of half, which is 1/4. Okay, and then we need to find K. Okay, so that is our purpose of the initial experiment of one slug. So mg is equal to ks. Okay, so m and the gravity is always 32. So the mass is one slug. So slug means 1 pounds times second square over feet. So that's a slug, right? Times the gravity is 32 feet over second square. So that's gravity is equal to spring constant we don't know. The stretch is 1/4. That is what we get from the experiment, because it stretched 3 inches and 3 inches is 1/4 feet. So if we simplify, you can see second square cancel out, feet goes away. So it's actually 32 pounds is equal to K times 1/4 feet. So K is 32 times 4 is 128 pounds over feet. So that's the spring constant. Okay, so it's always pound over feet, the spring constant. Okay, all right. Okay, then that's the spring constant. We determined it by the initial experiment. Okay, all right, so now we know we attach a half a slug. All right, okay, then what we need to know is W square, because the differential equation the second derivative of x plus W square, x is equal to 0, right? That's all. We just need the W. So W square is actually K over M. Now K we know 128 pound over feet, divide by mass is actually half a slug, so it's 0.5. So 125 divided by 0.5 is 256. So W square is 256. So our differential equation is 256 x is equal to 0. So this is what we are working with. Okay, so try to pause the video, try to do it by yourself, play with these units, try to convince how did I get this differential equation. Okay, all right, now all what we need to do is we need to solve it. So let's rewrite it and start new. Okay, all right, so we have the differential equation. Now the auxiliary equation will be m square plus 256 is equal to 0. So the roots are actually here plus or minus square root of negative 256, right? That is how you find the roots here. So here plus or minus square root of 256 is 16, square root of negative is I. So the root is plus or minus 16i. So we have two roots. Alpha is 0, here a complex root, beta is 16. So the solution is C1 times alpha is 0. So cosine beta is 16t plus C2 sine beta is 16 sine 16t. So this is the motion. Okay, and we saw it in the previous video too, right? But it's just we wrote our own auxiliary equation and we try to solve it like section 4.3. Okay, so if you are confused here, watch section 4.3 complex rules video again and pause this video, try to convince yourself, read the notes. Okay, that is why I do the same problems in the notes, so that you can read and watch and learn. Okay, now we have this motion, we got the solution, but really this is an initial value problem. Let's go on and learn why it is an initial value problem. See, now what happens is the mass is pulled down 3 inches and then released. What does that mean? What is the initial displacement? It is 3 inches, right? Or we can say x0. All right, so that's the first condition. At time is equal to 0, the initial displacement is 3 inches. 3 inches is actually 1/4 feet. So initial displacement is 1/4 feet. Okay. All right. And then the question says here, released with a velocity 1 feet per second. So 1 feet per second is the initial velocity. So how do you model velocity? X prime, right? The derivative of displacement with respect to time. So initial velocity at times equal to 0, initial velocity is 1. That was in feet and second American units. So these are the two conditions. So that is how you construct initial conditions. Okay, X prime is the velocity. So whenever a question is given, you have to construct the differential equation, you have to construct initial conditions as well. Now let's use them here. So if you use x0 is equal to 1/4, so that means t is equal to 0 and x is 1/4. So 1/4 is equal to cosine 0 is 1, sine 0 is 0. So c2 goes away. So c1 times 1 is c1. So c1 is 1/4 right away. Okay, all right, so let's use the second condition to find c2, but we have to find x prime. So x prime will be like, we have to differentiate this with respect to t. So 16 c1, derivative of cosine is negative sine 16t plus 16 c2 cosine 16t. Derivative of sine is cosine. Okay, this 16 comes out when you take the derivative. So now if you substitute 0 for time, x prime will be 1, sine 0 is 0, cosine 0 is 1, 16 times 0 is 0, cosine 0 is 1, so 16 c2. So c2 is 1/16. So our solution is really xt is equal to c1 is 1/4 cosine 16t plus c2 is 1/16 sine 16t. So this is the complete solution for the initial value problem. So given a time, you can find the displacement when you substitute it to here. Okay, all right, one more question. Now what is the amplitude of the motion? So the motion will look like this if you plot the motion. Okay, so I plot the motion in Mathematica. Okay, so you can see there's a periodic motion, right? So it's keep repeating. The motion will go forever because it is undamped. Now what is the amplitude? So what is the height of this motion, or the displacement from the rest position up or down? So what is either one? Okay, so what is this amplitude? So how do you find amplitude? Do you remember in last video we learned amplitude is c1 square plus c2 square root. So here c1 is 1/4, so 1/4 square, plus c2 is 1/16, so 1/16 square. So what we get is 1/4 square is 1/16, plus 1/16 square is 1/256. So if we take the common denominator to be 256, so this will be 17/256. How I got that? That you have to do it by yourself. Okay, I'm not spending time to add fractions. Basically I add these two fractions, multiplying this fraction by 16 top and bottom, so we get 16 times 16, 215 56 as the common denominator. Okay, so then we get square root of 17 over 256, which is square root of 17 over square root of 256 is 16, and this is the amplitude. Okay, so that is how you find the amplitude. After you use these initial conditions, after you figure out C1 and C2, you can find the amplitude. So that is how you really do a full problem. Okay, you construct, so typical problem, you have to find the spring constant by yourself. So there will be, most of the cases, there will be like an experiment. You attach, like in this question, you attach a one slug and you found the spring constant K. Then using K and mass, you can find W square. Then we come up with the differential equation model like this. So if it is a free undamped motion, we use the auxiliary equation method, and we found the roots, and we use the section 4.3 materials to write down the solution, and then we construct the initial conditions. The initial conditions are first the initial displacement, initial stretch, and then the second, the initial velocity. Both of them should be given in the question. Okay, now when I say the initial displacement, it is not coming from the experiment. It should come from the half a slug, right? From the second mass, the actual mass that you attach and you let the motion happen. Then using initial conditions, you were able to find C1 and C2 in the solution, and then using C1 and C2, we were able to find the amplitude by using this formula. So that is a typical thing that happens in free undamped motion. And one thing, what happens eventually? Nothing happens. The motion goes forever. Okay. All right. So in next video, we will learn a new type of a motion. Okay. Thank you.